Okay, we just talked about shear and moment values, internal loading values at a specific point along the beam. And now we're going to develop functions that would describe the shear and moment at any point along the beam. So my shear and moment functions are defined as the variation of shear and moment shear M, moment V, as a function of X, where X is the distance along the length of the beam. That means if you define these functions, you can find the shear and moment at any point along the length. And they are most helpful in designing if you need to know the maximum moment or shear, as well as eventually the shear and moment are used in, well, especially the shear in reinforced concrete design. We need to know how it varies along the length to determine if we need shear reinforcement or not, and if we can quit having reinforcement at some point. So what I'm looking for is shear as a function of X and moment as a function of X. Again, we're going to be ignoring axial because axial is not generally a significant force in your beam. Axial is generally in, what are they called? Columns. Yep, in columns. And very rarely will axial actually vary along the length unless you have some type of loading along the length of the beam, and axial loading, an applied one, discontinuity, or if your cross section changes over the length of the beam. The procedure for doing it, again, let's calculate our support reactions. Right, this is all for determinate beams, so we should be able to solve for those support reactions. Then separate the beam into different sections based off of changes in loadings that could lead to discontinuities. We'll show what that means in the example. Separate beam. Then we're going to draw a free body diagram of the beam up to that section cut. That is from your support to section cut. Or you could draw the individual section. You just have to know what's on the other side. You can only have unknowns on one side of your section. Right, determine your functions of each section as a function of the position. Right, position X along the length of the beam. And then at the very end, it's nice to do some checks, some sanity checks, right? The most basic is right. Check your values of your functions at known positions, such as you know what they should be at your supports. And if you have any discontinuities, you should verify that the different functions have the same value or have the same value or have the same, do not because of a specific reason. But it's always good to do some sanity checks at the end. Okay, so that's the basic thing. Now, just instead of finding it at one point, we're going to find it as a function along the entire length. So here's my beam. This is the same beam as before, but now I want to find the value or the function along the length, not just at a specific point. So I'm going to break my beam up into 3 different sections. And I'm going to break it up based off of discontinuities, which would be a change in load, such as a major change in load. Well, a change in, right? This concentrated force right here and this concentrated force right here. On one side, I'm going to have a different function than on the other side of each of these individual concentrated loads. So this is my section 1, this is my section 2, and this is my section 3. My section 1, if X starts from the left, my section 1 goes from X equals 0 feet to just before 3 feet, so not quite equal to 3 feet. But just before I apply that 50-pound load at 3 feet. Section 2 goes from 3 feet to just before that 25-pound load, which is 3 plus 4, so just before 7 feet. And section 3 goes from 7 feet to 10 feet. Technically, I'm going to put less than or equal to, because we got to get to the end. Okay, so let's look at section 1 first. I've got my shear and my moment, right? And X starts to the left. So sum of the forces in the Y direction. I have acting up, my reaction at A. Acting down, I have my shear. So if I solve for my shear, I get 42.5 pounds. Now you'll notice my shear doesn't have any, it doesn't care that I'm doing it along the length. It doesn't vary with the length at all, right? If I took it at X equals half a foot or X equals, right? This is from 0 to 3 feet. If I took it at, right, X equals like a half a foot or 2.5 feet, my value of my shear would be the same. Let's look at the moment at that section. I have, this is acting any distance X, 42.5 pounds, acting clockwise, so it's negative. So 42.5 pounds at a moment arm of X. And then I have my moment at X. So I solve for my moment at X. I get 42.5 pounds times X. Now, my moment varies with my length, right? If I wanted to find my internal moment here, 42.5 pounds times a half a foot is different than 42.5 pounds times 2.5 feet. So this moment function right here is going to vary linearly. That's for my first section, right? I'm going to go to section 2, which is from 3 feet to 7 feet. Again, I have my moment and shear function. If I do some of the forces in the Y direction, acting up, I have my 42.5 pounds at my reaction. Then I have my 50 pounds acting down. And my shear acting down. Solve for shear. My shear function is negative 7.5 pounds. Again, my shear function, right? I already did it from here to here, but if I'm talking about from here onwards, if I have an X value of 3.5 feet, it's going to be negative 7.5. If I'm looking at 6 feet, it's going to be negative 7.5. So this one again is not varying, it's constant. Let's look at the moment. If I'm looking at the moment right here, I've got 42.5 pounds acting at a distance X, and it's acting clockwise, so it's negative. I've got 50 pounds, and if I'm looking at the distance from here, it is X minus 3 feet. So, right, if this distance is X, that's X minus 3 feet. And it is acting counterclockwise, so it's positive. A force of 50 pounds at a moment arm of X minus 3 feet. And then I've also got my moment function acting positive counterclockwise. If I solve for my moment, I get 42.5 pounds times X minus 50 pounds times X minus 3 feet. If I simplify that, 42 minus 50 minus 7.5 pounds times X, 50 times 3, that's 150. Negative plus negative is a positive, so 150 foot-pounds. Okay, I'm going to give you guys 5 minutes to do section 3. Okay, I'm gonna go on and finish this, so if you haven't done it, pause, and then we can check and see if you guys got it right. So I'm looking at x is equal to 7 feet to 10 feet, right? Go back and look. 7 feet to 10 feet. My shear function, my moment function. Let's look at the sum of the forces in the y direction. I've got my 42.5 pounds acting up, my 50 pounds acting down, my 25 pounds acting down, and my shear acting down. So if I solve for shear, I get 42.5 pounds minus 50 pounds minus 25 pounds. And again, I get a constant value, which is equal to negative 32.5 pounds. That value might look familiar. We're going to do a little summary check, see why that value is significant. If I do the sum of the moments about this section, all right, that's a positive. I've got 42.5 pounds. Gotta get this out of the way. Sum of the moments. Right, this is acting at a distance x, right? So x times 42, that's a clockwise, so it's negative. Then I have my 50 pounds, which is acting at x minus 3 feet. And it is going this counterclockwise, right? This way and down. So it's positive. And then my 25 pounds, that is acting at, let's see if I can, right, this is x minus 3 feet. This is x, this is x minus 7 feet. So I've got my 25 pounds right down, so it's counterclockwise. X minus 7 feet, and then my moment, which is also positive. So if I solve for my moment, I get 42.5 pounds times x minus 50 pounds times x minus 3 feet minus 25 pounds times x minus 7 feet. If I add those all up, all my x's, I get 42.5 minus 50 minus 25. So you should get minus 32.5 pounds x, and then negative 50 times negative 3 is 150. Negative 25 times negative 7 is what? 175? Yeah. So add it together, you should get 320 foot-pounds. Now I'm going to make a little summary. All right, let's do a little summary. If this is my section, my 3 different sections, right? Here's my beam. I'm going to go back and write 3 different functions. From 0 to 3, my shear is 42.5 pounds. From 3 to 7, it's negative 7.5 pounds. From 7 to 10, negative 32.5. And if I want to do the same thing for my moment, I've got 42.5 pounds times X. For 0 to 3 feet. And again, we're making it not equal to at the 3 feet because we're assuming it's ending right before I apply that a 50-pound load. Negative 7.5 pounds times X plus 150 feet for my second section. That's from 3 feet to 7 feet. Oh, geez. And my final one, negative 32.5 pounds times X plus 325 pounds, foot-pounds. Okay. So that's writing out the actual equations for my shear and moment functions along the length of this beam. Now let's do a little sanity check, right? First of all, let's look at support A. Support A is where X is equal to 0. So my shear at X equal to 0 is 42.5 pounds. Which, oh look, that's the same as my support reaction, right? It's as if we took a little, right, X equals 0. Little bitty, tiny, we're right next to the support, right? And that's our shear. Our shear at X equal to 0. Now, what is my, sorry, I'll give you guys a second. if you wanted to draw that little thing. Now, what is my moment at x equal to 0? 42.5 pounds times 0 is 0. And that makes sense because this is a pin and it has no moment reaction. So it better be 0, right? Same thing, let's look at my support on the other side, right? Support B, that's where x is equal to 10 feet. My shear at x is equal to 10 feet is minus 32.5 pounds. Which again, if I'm looking right at support B, if I go back and look at my sign convention, it's like that. Oops, sorry. It's acting downward because it's negative, but it's because I'm drawing it that way. All right. It's not acting down because it's negative. It's acting down because if I go back to my sign conventions, down is positive if up is positive if I'm looking at the left side. The right side, good Lord. If I'm looking at the right side from the support. Down is positive if I'm looking at from the support this way. Positive. Up is if I'm looking from the support that way. So that is why it is negative and is acting downwards, not simply because it is acting downwards. So I want to take a minute, think about that. Right. I could also, like, that's the easiest check, right, to do. Could also look at a discontinuity, which would be, like, let's look at x equal to 3. Right, that's where I had to make a break, right? X equal to 3. If I look at my shear from my first, just before I get to 3, the first section, V at x equal to 2.99999, I get 42.5 pounds. If I look x directly after I apply that load, or right as I apply that load, x equal to 3 feet, I get negative 7.5 pounds. The difference, if you add those two together, 42.5 plus 7.5 is 50 pounds, right? Makes sense. You add a 50-pound load, your shear is going to change by 50 pounds. However, I didn't apply a moment, so if I take my moment at x equal to 2.9999, or basically 3, use the first equation, 4.25 times 3, I get 127.5 pounds-feet, and my moment right at that discontinuity, negative 7.5 times 3 plus 150, I get 127.5 pound-feet or foot-pounds. It just means I have a discontinuity in my shear due to a concentrated force, but I don't have a discontinuity in my moment because I don't have like a concentrated force. I don't have something interjecting right there to cause a jump or a sudden change in my moment. And you can do the same thing at, just for your sanity check, at x equal to 7 feet using the second two sets of equations. You see 32.5 minus 7.5, well that's 25 pounds. Yep, because you applied a 25-pound load. All right, these two, the difference is 25 pounds. And similarly, if you found the moment at 7 feet for these two equations, you would get a value that was the same. Okay? So we can work on a second example. Right here, the only difference is I have this applied load, and but again, I'm going to break it up, right? The discontinuity is I have an applied load, and then I don't, and then nothing, nothing, nothing. I applied a concentrated load. So again, I'm going to break it up into 3 sections. As long as the distributed load function doesn't change, I don't have a discontinuity. So let's look at the first section. This is happening from, right, again, we have 0 to 3 feet, from 3 feet to 7 feet. This is a little alligator, right? Is that what you guys learned in like elementary school? The alligator, it wants to eat the bigger number. And then 7 feet to 10 feet. So let's look at from 0 to 3 feet. Some of the forces in the y direction. Oh, I didn't draw my, complete my thing. V of x and m of x. Right? So let's see. Acting in the y direction, I have 33 pounds up. I have this, which the resultant is 10 pounds per foot times x. All right, the length of this being x. So I have acting downwards, 10 pounds foot times x, and then also acting down my shear. So my shear function, if I solve for it, is 33 pounds minus 10 pounds per foot times x. Now I'm going to solve for, I didn't write my little up plus. You don't have to draw that if you don't want. It's just more of a reminder. If I do the sum of my moments is equal to 0, my sum of my moments here, I get my 33 pounds acting at a distance x, which makes it clockwise, so it's negative. Then the resultant of my distributed load is acting at a distance x over 2, right? The whole distance is x, so I just divide it by 2. And it is acting counterclockwise, so it's positive. 10 pounds per foot times x is the force, and it's acting at a distance x over 2. That's a little multiplication right there. And then my other moment is the moment at the section, which is m of x, and it's positive. So if I solve for m of x, I get 33 pounds times x minus 10 pounds per foot, x squared over 2, or if I solve that, if I simplify it even more, £33 times x minus 5 pounds per foot times x squared. So you might notice now with a distributed load, with a linearly distributed load, I have a linear relationship between shear and my variable x, and then a quadratic relationship between my moment and the length x. Might be noticing a couple patterns. We'll talk about that in a minute, but yes, there's a pattern. So, I want you guys to solve section 2 and section 3. I'm going to give 5 minutes, but if you don't finish it, just pause before that happens, before I go on. Excuse me. Hope I didn't startle you. All right, it's been 5 minutes. So I'm going to do sections 2 and 3. If you haven't completed them, just pause. All right, section 2. We have our shear function and our moment function. Let's see. Some of the forces in the y direction. We have our 33 pounds acting up. I don't know why I put that in parentheses, but the resultant of this force, which is 10 pounds per foot times 3 feet, or 30 pounds, acting downwards. And then also acting downwards, we have our shear function. Solve for that. We get 33 pounds minus 10 pounds per foot times 3 feet, or 3 pounds. My L's and my 1s are not. There, 3 pounds. So let's look at the moment. We've got, right, if this is a distance x, then we have 33 pounds making clockwise, so it's negative 33 pounds times x. The resultant of the distributed load is acting at a distance of, right, if this part is 3 feet over 2, then this is x minus 3 feet over 2. So I have acting counterclockwise, which is positive. I have the resultant of the distributed load, right? 10 pounds per foot times 3 feet, acting at a distance from this section right here, x minus 3 feet over 2. plus my moment. Solve for my moment. I get 33 pounds times x minus 10 pounds per foot times 3 feet times x minus 3 feet over 2. And if I simplify that, I get m over x equals 33 pounds minus 10 times 3, so 3 pounds times x plus 10 times 3 times 3 over 2, which is 45 foot-pounds. Hope you all look at those answers. And if I go to section 3, again, I have my shear and my moment. When you're doing your homework, these little sections will not be drawn for you, so please draw them yourself. I just figured we're not going to waste time drawing stuff, right? Some of the forces in the y direction. I've got 33 pounds up. This is still 30 pounds, right? 10 pounds per foot times 3 feet, or 30 pounds. And my 25-pound concentrated force. And then my shear. So if I solve for that, I get 33 pounds minus 10 pounds per foot times 3 feet minus 25 pounds, which should give me minus 22 pounds. And finally, I get my moment. So let's see, I'm going to think about my moment arms. So this one is going to be acting at a distance x. If this is 3 feet divided by 2, then this is acting at a distance x minus 3 feet over 2. And this is acting at a distance x minus 3 feet plus 4 feet, which is 7 feet. So I do the sum of my moments. I get acting clockwise, which is negative, my 33 pounds times x, the resultant of my distributed load, which is 10 pounds per foot times 3 feet acting at x minus 3 feet over 2, and that's positive because counterclockwise. And then I have also acting counterclockwise positive is this 25 pounds acting at x minus 7 feet. And finally, my moment at my section. solve for my moment at x, I get 33 pounds times x minus 10 pounds per foot times 3 feet times x minus 3 feet over 2 minus 25 pounds x minus 7 feet. If I simplify that, 33 minus 30 minus 25, I should get minus 22 pounds x plus 30 times 3 over 2, that's 45. And 25 times 7, which is 175, so that's 220. So if I do a little summary, right, I've got 33 minus 10 pounds. I'm just, you guys can go back and look, but, right, negative 10 pounds per foot. Let me see if I can make that a little bit better. Minus 10 pounds per foot. X plus 33 pounds for 0 to x equals 3 feet, or just before 3 feet. And then it's constant after that, right? 3 pounds for 3 feet to 7 feet, and minus 22 pounds for 7 feet to 10 feet. My moment, I've got minus 5 pounds per foot times x squared plus 33 pounds times x for 0 to 3. Let's see, 3 pounds times x plus 45 pounds feet for 3 feet to 7 feet, and minus 22 pounds x plus 220 pound feet for 7 feet to 10 feet. Do another little check, right? I'm gonna look at my support at A. So x equal to 0, right? Shear at x equal to 0 is 33 pounds, which makes sense because that's my vertical reaction. If that vertical reaction was down, then that shear would be negative, not simply because the vertical reaction is down. But because that's my sign convention. My moment at x equal to 0 is 0, which is good because it's a pin. If I go look at my support B, where x equals 10 feet, oops, my shear at x equal to 10 feet is minus 22 pounds. Which makes sense because I have my 22 pound reaction right there. And my moment at x equal to 10 feet is minus 22 times 10 plus 220, 0, which is also good because that's a roller. So if excuse me, you could also go check your discontinuities, make sure you don't have any applied concentrated moments, so you shouldn't have any discontinuities in your moments. So check at x equal to 3 and x equal to 7 that the moments are the same. Check that your difference, right, from here to here, yep, that's 25 pounds. So at x equals 7, you have that discontinuity there due to the concentrated load. And that's how you can solve for shear and moment functions along the length of the beam. Break it up into sections based off of changes in loading. And draw a free body diagram for each different section. Find your shear and moment function for each section. And then at the end, write it all down and do a couple little sanity checks to make sure what you got makes sense. All right. Thanks.